Hello everyone, welcome to this video. In the previous video, we saw what is the Parseval's theorem. Now let us see how we can apply this theorem. So for that, let me discuss a question. The question says you are to apply the Parseval's identity to the given function f of x is equal to x in the interval minus pi to pi. This is given to be the closed interval, right? Closed from the right hand side and open at the left hand side. Why? Because this is periodic function and you are to deduce that you have pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus so on. So that means you have the term of this kind, 1 by n square kind. So for that, in order to apply the Parseval's identity, what you should know that this function, first of all, which form of Parseval's identity should I use here? So is there some particular cases which I could use here? So if you look at this function is an odd function in the given interval. Therefore, you know what is the Parseval's identity? The Parseval's identity for the odd function that is given by 1 by 2 pi integration minus pi to pi f of x whole square dx. This thing is equal to 1 by 2 summation n varies from 1 to infinity dn square. So that means you are only required to compute this integration over here, and you just have to know what is the value of this coefficient bn here for the given function. So here you already know that what is bn. The formula for bn, which is given by the half range sine series, that is given by 2 divided by the length of interval, half of length of interval, that is pi, integration from 0 to pi in the half interval, right, from 0 to pi, f of x sine nx dx. So this is your bn. So now your function that is given to be f of x is equal to x. So let me first calculate this bn. So this bn could be calculated when you substitute the function's value here. The function's value is x. So we have x into sine nx dx. So we have to perform this integration. So for that I can consider this to be the first function and this to be the second function. So that we have first function as such, the integration of second is cos nx divided by n, right, minus the derivative of first, that is 1, integration of second is minus cos nx upon n, right, its integration again from 0 to pi. So when you perform this integration again, you have, and here also we have to substitute the limits. So when you substitute the limit here, this 2 by pi would come as such. So when you substitute the lower limit, this term would be 0. When you substitute the upper limit, it would be pi by n into minus cos n pi, right? And when you perform this differentiation, you have two negative signs, so it becomes positive, and you have sine nx divided by n square. And here you also have to write down the limits of integration. So that you would be getting, for the first term, the value would be minus 2 by n, the value of cos n pi, that is minus 1 raised to power n, right? And here when you substitute the upper limit, you will have sine n pi, which is equal to 0, and when you substitute the lower limit, you have 0 again. Therefore the second term is equal to 0. So from here you obtain the value of bn as minus 2 upon n into minus 1 to the power n. So this is your bn. The next thing that is required is we have to use this equation. So let me call this as star. So we have to solve the left hand side for this equation star. So now, or let me rewrite this equation first. So when you rewrite this equation, you have 1 by 2 pi as such. So that means the left hand side would be as such. 1 by 2 pi integration from minus pi to pi. The integration of the function square dx, that is equal to 1 by 2 summation dn whole square. 1 by 2 summation n varies from 1 to infinity. Dn is minus 2 upon n minus 1 raised to power n, its whole square. So this becomes equal to the term. Here you could solve this square, so you have 1 by 2 as such, summation n varies from 1 to infinity, right? So you have 4 by n square and you have minus 1 raised to power 2n. Now this is an even thing, and when you take the even power of minus 1, it becomes equal to 1 only. So we have here 1 only, right? So this is what you have here. And moreover, you can take this 4 outside, so that you have 1 by 2 pi integration minus pi to pi f of x whole square dx, that is equal to 2 summation n varies from 1 to infinity 1 by n square, right? Now what you have to do, you have to again substitute the value of your function. The function's value that is given to be x, so we will utilize it here, so that it becomes 1 by 2 pi integration minus pi to pi x square dx, that is equal to 2 summation n varies from 1 to infinity 1 by n square. So when you perform this integration, you have x cube from varying from, the limits varies from minus pi to pi, right? And you have 1 by 2 pi as such is equal to 2 summation n varies from 1 to infinity 1 by n square. So that when you substitute the limits here, you have 1 by 3 would be taken out, so you have 1 by 6 pi. So you have pi cube minus of minus pi cube, right? And here on the left, on the right hand side, you have the term as such. So now this becomes 2 times of pi cube. So you have pi square divided by 3, that is equal to 2 times. You could expand this term so that you have 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus so on. So in other words, you could also shift this 2 to the left hand side, so that you would have pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus so on, right? So this is what you wanted to prove here in the given question. So let me show you this thing once more. So in the given question, you wanted to prove this thing, right? So I hope you understood this concept of Parseval's theorem and how to apply it. Well, I'll see you in the next one.